There is a star about 1,400 light-years from Earth, sitting quietly in the constellation Cygnus, that broke astronomy. Not in a dramatic, explosive way. Not the way a supernova breaks things or a gamma-ray burst. It broke astronomy quietly, the way a really good mystery breaks you, slowly, through accumulation, through the gradual realization that everything you thought you understood about how stars behave is not enough to explain what this one is doing. It is a star that dims. Not the way stars are supposed to dim. Not the clean, predictable, mathematically precise dimming of a planet passing in front of it, but in ways that are irregular and asymmetric and deep and sometimes prolonged and sometimes brief and never quite the same twice and never. In the entire database of observations from one of the most powerful planet-hunting telescopes ever launched, seen in any other star out of the 150,000 stars that telescope was watching simultaneously. One star, doing something no other star does. And the story of how it was found, and who found it, and what happened after, is one of the most human stories in the history of modern science. The telescope responsible for the discovery was Kepler. Not the 17th century astronomer, the spacecraft. The Kepler Space Telescope was launched by NASA in March of 2009, with a specific and singular mission: stare at a fixed patch of sky containing roughly 150,000 stars, and look for the tiny dips in brightness that indicate a planet passing in front of its star. When a planet crosses the disk of a star as seen from Earth, a transit, it blocks a small fraction of the star's light, causing the star to appear to dim slightly, briefly, regularly. The dimming caused by an Earth-sized planet transiting a Sun-sized star is only about 0.01%, 1 part in 10,000. And it repeats on the precise schedule of the planet's orbital period. Kepler was built to detect signals this small, this regular, this precise. It was a machine designed to find patterns, and it was extraordinary at its job. In nearly a decade of operation, Kepler found thousands of exoplanets, worlds orbiting distant stars, and completely transformed our understanding of how common planets are in the galaxy. But Kepler produced more data than any team of professional astronomers could analyze alone. The telescope was watching 150,000 stars simultaneously and recording their brightness measurements every 30 minutes, generating a dataset of staggering size and complexity. The Kepler team at NASA and affiliated research groups processed the data with algorithms, automated systems that looked for the specific signature of a planetary transit and flagged promising candidates for follow-up. These algorithms were good, but algorithms are designed to find what you tell them to find. They find patterns that match the pattern you define. They are very good at finding planets. They are not necessarily good at finding something that has never been seen before, something no one thought to define a pattern for, something that does not fit the template. For that, you need eyes, human eyes. People looking at the actual data and noticing that something is wrong even when they cannot immediately articulate what is wrong, or why, or what it means. You need pattern recognition that is not constrained by prior assumptions about what patterns are possible. This is the origin of Planet Hunters. Planet Hunters is a citizen science project launched in 2010 as part of the Zooniverse platform, a web-based system that allows ordinary members of the public to contribute to scientific research by classifying and analyzing data that would otherwise take professional researchers years or decades to get through. The interface for Planet Hunters was simple. Volunteers were shown light curves, graphs of a star's brightness over time, and asked to mark any features that looked unusual, particularly dips that might indicate a transiting planet. The volunteers received no pay. They received no academic credit. They were people who found the work interesting and wanted to participate in something larger than their ordinary lives, sitting at home in the evenings and on weekends, clicking through light curves one by one, marking what they saw. Tens of thousands of people participated. A schoolteacher in Arkansas, a retired engineer in Germany, a software developer in Australia, an insurance claims adjuster in Iowa. They had widely varying levels of scientific background and widely varying amounts of time to contribute. What they shared was curiosity and attention, and the combination of tens of thousands of curious, attentive people turned out to be remarkably powerful. Planet Hunters volunteers discovered planets that the automated Kepler algorithms had missed. Not many, but some, and genuine ones. More importantly, they noticed things the algorithms were not designed to notice. Edge cases, anomalies, stars that behaved in ways that were not obviously a planet, but were obviously not normal either. The volunteers flagged these as interesting, discussed them in the forum section of the site, argued about them, and brought the most puzzling ones to the attention of the professional astronomers overseeing the project. In 2011, not long after Planet Hunters launched, several volunteers independently flagged a star with an unusual light curve. The star's catalog designation was KIC 84628522, which is about as evocative as a phone number. The light curve showed some kind of dipping behavior that was clearly not the clean, symmetric, regular pattern of a planetary transit. It was messier than that, more complicated, harder to characterize. The volunteers did not know what it was. They knew it was weird. They called it, among themselves, a bizarre star. One volunteer called it interesting in the forum, and several others agreed. The flag went up, and it sat in the growing pile of anomalies that the citizen science project was accumulating. The professional astronomer on the Planet Hunters team who eventually looked at this pile of anomalies and started trying to figure out which ones were genuinely interesting and which ones were data artifacts or known phenomena was a postdoctoral researcher named Tabetha Boyajian. Tabetha Boyajian, Tabby to everyone who knew her and to most of the internet after the story broke, was at Yale at the time, working in the field of stellar astrophysics. She was not specifically a SETI researcher. She was not someone who spent her days thinking about extraterrestrial intelligence. She was a scientist who studied stars, and her job in the Planet Hunters collaboration was to follow up on the anomalous candidates the volunteers found and figure out what they were. When she looked at KIC 84628522, she did not immediately know what she was seeing either. What she saw was a light curve unlike anything in the Kepler database. Over the approximately 4 years that Kepler had been watching this star, it had dimmed on multiple occasions by amounts that were extraordinary. Not the fractional percent dimming of a planet transit, not even the slightly larger dimming of a large exoplanet. The deepest dips were 15 to 22%, the star losing 15 to 22% of its total light for periods of days to weeks. This is a number that should cause you to stop and reread it. A dimming of 1% caused by a planet transit is considered significant. A dimming of 1.7% caused by a Jupiter-sized planet, the largest planet in our solar system, is among the largest transit signals a planet can produce around a sun-like star. KIC 84628522 was dimming by 15 to 22%. Whatever was blocking its light was not a planet. A planet could not do this. Nothing in the standard inventory of known astrophysical phenomena affecting sun-like stars could do this. Tabby Boyajian stared at the light curve and could not explain it. She did what good scientists do when they encounter something they cannot explain. She looked harder and involved more people. She brought the data to colleagues. She talked to stellar physicists, to planet hunters, to people who studied variable stars and stellar flares and binary systems and circumstellar disk structures. She asked everyone who had a possible explanation to put it on the table. The result of this process was a scientific paper, published in 2015 in the monthly notices of the Royal Astronomical Society, with Boyajian as the lead author and a long list of co-authors that included many of the Planet Hunters volunteers who had flagged the star in the first place. This was not a common arrangement, citizen science volunteers appearing as co-authors on a peer-reviewed astronomy paper, but it was the right arrangement, because the discovery genuinely belonged to them. They had found it. The paper examined the light curve in detail, considered every conventional explanation the team could think of, ruled out or found problems with all of them, and concluded, carefully, hedged with appropriate scientific caution, that the behavior of KIC 84628522 was unlike anything previously seen and was not easily explained by any known natural phenomenon. The paper did not use the word aliens. Boyajian's paper was scrupulously careful about that. It listed hypotheses in order of increasing exoticness and decreasing likelihood, starting with the most mundane, instrumental artifacts, which were ruled out because the signal was real and consistent across different analysis approaches. Then nearby objects creating a chance alignment, ruled out by additional observations. Then a swarm of comets, which was one of the leading natural explanations and remained on the table as the best available conventional hypothesis. Then, at the end, almost as a footnote but present and explicit, the paper mentioned that if the conventional hypotheses all failed, the light curve was consistent with a large swarm of artificial structures. The paper cited a specific theoretical paper from 1960 by physicist Freeman Dyson, who had proposed that an advanced civilization might dismantle a planet and use its material to build a vast structure around its star to collect maximum solar energy. A Dyson sphere, or partial Dyson swarm. The paper did not say this was the explanation. It said carefully that the data was consistent with it. That footnote was enough. The paper was submitted in September 2015. Before it was even formally published, word had gotten out. Astronomers talked to each other. Preprints circulate. And one of the astronomers who read the preprint was a man named Jason Wright, a professor of astronomy at Penn State University who had a specific and unusual area of expertise. He had spent years thinking about what technological civilizations might look like from the outside, what signatures an advanced alien civilization might leave in astronomical data, and what surveys astronomers might design to search for those signatures. Jason Wright read Boyajian's paper and recognized immediately that what she had described was exactly the kind of light curve that a partial Dyson swarm, a structure of artificial collectors orbiting a star, would produce. Not because he had ever expected to see one, but because he had thought carefully about what one would look like if it existed, and the answer to that question looked like this. Wright reached out to Boyajian. They had a conversation that eventually became a collaboration, and that collaboration produced a second paper, what the press and the internet would eventually describe as the alien megastructure paper, which examined the Dyson swarm hypothesis in more technical detail. It was serious. It used real physics. It did not claim that the star had an alien megastructure. It argued that the hypothesis was consistent with the data and should be taken seriously as a scientific hypothesis alongside the natural explanations, all of which had their own problems. Wright knew what he was doing. He knew that floating the word alien in a scientific paper about a real star currently being observed by Kepler was going to produce a reaction. He said later that he agonized over the language. He was a serious scientist in a field, SETI, that already struggled for mainstream respect, and he did not want to be the person who was remembered for claiming aliens when it turned out to be comets. But he also thought the hypothesis was genuinely on the table, and intellectual honesty required saying so. The reaction was everything he had both hoped for and feared. The paper hit the internet in October 2015. The Atlantic published an article about it under the headline, "The Most Mysterious Star in Our Galaxy," and within 24 hours the story had crossed from the science press into the general media, then into social media, and then into a cultural moment. The most mysterious star, the alien megastructure, KIC 8462852. The story was everywhere. Tabby's star, the nickname the internet settled on after Tabitha Boyajian, was suddenly the most talked about object in the sky. Morning television programs mentioned it. Late-night hosts joked about it. Twitter devoted entire threads to it. The phrase alien megastructure appeared in headlines in dozens of languages. For a brief period in the autumn of 2015, a star catalog number that no one had ever heard of was more famous than any planet NASA had ever announced. The professional astronomical community had mixed feelings about this. On one hand, the public enthusiasm for the story was extraordinary, and anything that gets people excited about astronomy is broadly good. On the other hand, the coverage was consistently irresponsible about the distinction between the data is consistent with this hypothesis and scientists have found evidence of aliens, and the nuance was lost within hours of the story breaking. By the time it reached most people's feeds, the story had been simplified to, there might be aliens around a star 1,400 light-years away, and NASA knows about it. This was not quite what the papers had said, but it was what the moment needed, apparently. And the moment was enormous. In the weeks and months that followed, the scientific community mobilized around Tabby's star in a way that is itself remarkable. Telescopes were pointed at it. Archives were searched for historical data predating Kepler. Amateurs around the world set up their own monitoring campaigns. The SETI Institute used the Allen Telescope Array, a dedicated radio telescope facility designed for SETI observations, to listen to KIC 8462852 for radio emissions. No radio signal was detected. This did not rule out the alien hypothesis. An alien civilization would not necessarily broadcast in radio, and even if it did, we might not be in the direction of the beam, but it was a data point. Professional observatories applied for telescope time and got it, motivated by the combination of genuine scientific curiosity and, in some cases, the awareness that whatever was going on around this star was interesting regardless of whether aliens were involved. The historical data search was particularly fascinating. The Kepler dataset only went back to 2009, but there were older photographic plate archives, collections of actual glass plates on which observatories had photographed the sky going back more than a century. And if KIC 846285 had been dimming not just during the Kepler era but for decades before, that would be a significant clue. A researcher named Bradley Schaefer at Louisiana State University examined digitized scans of the Harvard Plate Collection, one of the most extensive photographic archives in astronomy, containing over 500,000 glass plates accumulated over more than a century of observations from the Harvard College Observatory, and compared the brightness of KIC 846285 across decades of archival images. What he found was striking. The star appeared to have been fading slowly over the entire 20th century, dimming by about 20% between 1890 and 1989. Not the dips that Kepler saw, the dramatic, days-long dimmings of 15 to 22%, but a long, slow secular fading across 100 years of data. This was significant for multiple reasons. First, it extended the anomalous behavior back far beyond the Kepler era, indicating that whatever was happening to this star was not a recent development. Second, it made the cometary swarm hypothesis, already the leading natural explanation for the Kepler dips, more difficult to sustain, because a swarm of comets would produce short-term dipping events but would not easily explain a century-long secular fading. And third, it was one more data point that did not fit any single clean explanation. Nothing on the table accounted for both the short-term dips and the long-term fades simultaneously in a way that satisfied the physics. This point became somewhat contested. Another analysis of the historical data by Benjamin Montet and Joshua Simon using a different archive and different methods confirmed the secular fading during the Kepler era itself. The star had faded by about 3% over the approximately 4 years of Kepler observations, in addition to the sharp short-term dips. This Kepler-era fading was real and not an artifact. But Schaefer's century-long historical result was questioned by other researchers who examined the plate archive and found the calibration of photographic plates from different decades to be uncertain enough that the century-long trend might not be real. The debate over the historical data has not been fully resolved and remains a point of active disagreement among the researchers who have worked on it. What the community needed, above all else, was to catch the star dipping in real time, to have telescopes of various kinds watching KIC 846285 at the moment one of its mysterious dimmings began, so that the dip could be studied across multiple wavelengths simultaneously, rather than reconstructed after the fact from the Kepler data. The Kepler data was photometric. It measured total brightness, but it could not tell you whether the dips were the same at all wavelengths, or whether some wavelengths were affected more than others. This distinction is enormously important, because different physical causes of dimming have different wavelength dependencies. A solid, opaque object, a planet, a rocky structure, a swarm of debris, blocks all wavelengths of light equally. But dust blocks short wavelengths of light more efficiently than long wavelengths, which is why sunsets are red. The atmosphere scatters short wavelength blue light more than long wavelength red light, so blue light is removed preferentially and the remaining light is red. If the dips of Tabby's star were caused by dust, they would dim the star more at blue wavelengths than at red wavelengths. If they were caused by solid opaque objects, the dimming would be the same at all wavelengths. Getting multi-wavelength observations of a dip in real time was the key experiment that could distinguish between dust and solid objects. The problem was that the dips were unpredictable. They did not follow a regular schedule like a planetary transit. They came at irregular intervals, sometimes with months between them, sometimes closer together. You could not know in advance when the next dip would begin. You had to monitor the star constantly and be ready to call the major telescope facilities immediately when a dip started, sending the alert that would interrupt their scheduled observing programs and get the big instruments pointed at KIC 846285 before the dip ended. This is where Boyajian made a decision that was creative and somewhat unusual for academic science. She turned to crowdfunding. She launched a campaign on the platform Kickstarter to raise money for a dedicated monitoring campaign for Tabby's star, funds that would go toward telescope time on a network of small, flexible observatories that could watch the star constantly and be supplemented by larger facilities when a dip began. The campaign raised over $100,000 from more than 1,700 backers, which is an unusual funding mechanism for astronomical research. It reflected both the broad public interest in the star. The same public that had made alien megastructure a trending topic on social media was willing to put money toward figuring out what was going on, and a genuine gap in how major telescope facilities work. Big observatories operate on scheduled programs approved well in advance. They are not nimble. Catching an unpredictable dip in a specific star requires the kind of constant monitoring that small, dedicated facilities do better than big ones, and those facilities needed resources. The monitoring campaign ran. Months passed. The star was watched. And then, in May of 2017, it dipped again. The alert went out. Telescopes around the world, primed and waiting, swung to KIC 8462852 and began collecting data in multiple wavelengths simultaneously. The dip lasted for days. It was followed by more dips over the following weeks, a cluster of activity that gave observers extended time to gather data across the event. It was the opportunity the community had been waiting for since 2015. When the data from the 2017 dipping events was analyzed, it gave a clear answer to the wavelength question. The dimming was not the same at all wavelengths. Blue light was extinguished more than red light. The chromatic signature of the dips was consistent with dust, specifically with fine particles smaller than the wavelength of visible light, which scatter short wavelength light more efficiently and produce the reddening effect seen in the data. This was a significant result, and it was one of the most important findings the Tabby star investigation had produced, because it changed the shape of the debate in a clear direction. Solid, opaque objects, rocky structures, metal swarms, the components of a Dyson sphere, would not produce this chromatic signature. Dust would. The 2017 dipping events looked like dust. This was not by itself a complete explanation. Dust around stars is not unusual. Many young stars have dusty protoplanetary disks, and some older stars have debris disks from collisions between planetesimals. But the geometry and behavior of the dust around KIC 8462852 did not fit neatly into any known category of dusty stellar environment. The dust would have to be arranged in specific irregular clouds in specific orbital configurations to produce the dipping pattern seen over the Kepler era. It would have to be in a location, the zone around the star where temperatures would be expected to sublimate fine dust particles fairly quickly, where its persistence over years of observations was somewhat unexpected. And none of the dust-based natural explanations fully accounted for all the features of the light curve: the short-term dips, the secular fading over years, the highly irregular shapes of the individual dips, and the total absence of the infrared excess that warm dust should produce. That last point, the infrared, is worth dwelling on. Dust around a star absorbs starlight and re-radiates it as heat, producing an infrared excess above what the star itself emits. When astronomers looked at the infrared emission from Tabby's star, they found it was not obviously elevated above what the star alone would produce. A large amount of warm dust, enough to block 15 to 22% of the star's light, should produce a detectable infrared signature. The infrared data did not clearly show this. Some researchers argued that cold dust, far from the star, could absorb and re-radiate at very long infrared wavelengths where detection is harder. Others found this explanation strained. The infrared non-detection remained one of the most awkward features of any dust-based explanation, and it kept some researchers from fully committing to dust as the answer even after the 2017 chromatic data came in. The scientific literature on Tabby's star has grown to dozens of papers proposing dozens of different hypotheses, debating the merits of each, and in most cases reaching the honest conclusion that the problem is not solved. Among the natural explanations that have been seriously proposed, the swarm of comets or cometary fragments is the most durable, despite its problems. The idea is that a family of comets or the fragments of one or more large disrupted comets is orbiting Tabby's star in a cloud or stream, and as these objects cross our line of sight, they block portions of the star's light. The irregular shapes of the dips would reflect the irregular distribution of cometary material along the orbit. The dust produced by the sublimating comets would be the dusty material producing the chromatic signature in 2017. But the amount of cometary material required is enormous, far more than any known cometary population around any star, and the physics of keeping it in the right configuration to produce the observed pattern is not trivial to work out. Another proposal involves the aftermath of a planetary collision, a massive impact between two large rocky bodies in the inner part of the Tabby's star system, producing a cloud of debris and dust that is gradually spreading and evolving. This can produce dust, irregular structure, and potentially the secular fading if the debris cloud is spreading to cover more of the stellar disk over time. But matching the fine details of the Kepler light curve with a specific collision model is difficult, and the model makes predictions about the infrared that are not obviously consistent with the observations. More exotic natural explanations include a ringed substellar object, something like a planet with an extremely large and complex ring system, far more elaborate than Saturn's, possibly including rings of captured dust or debris. The transit of such an object across the stellar disk could produce asymmetric, irregular dipping if the ring system is tilted and has gaps and clumps. But the ring system needed to produce the deepest dips would be extraordinary, far beyond anything seen in the solar system or around any known exoplanet. There have also been proposals involving the star itself, rather than something in front of it. Could the star be intrinsically variable in some unusual way? Could magnetic activity, star spots, or some unusual internal process cause it to dim and brighten in the patterns observed? Most researchers have concluded that KIC 8462852's stellar type, an F-type star, a bit larger and hotter than our Sun but not dramatically different, makes extreme intrinsic variability of the observed magnitude unlikely. Ordinary F-type stars do not behave this way. But unlikely is not impossible, and the intrinsic variability hypothesis has not been completely ruled out. And then there is the alien hypothesis, still. The chromatic data from 2017 disfavors solid opaque structures. The material blocking the starlight is dusty, not solid and opaque, but an alien megastructure that was actively shedding dust, a construction project in progress, perhaps, or structures that are disintegrating over time, would produce exactly the kind of dusty, chromatic dimming signal that was observed. The dust could be a byproduct of construction, or of the slow deterioration of ancient structures, or of mining operations on a scale that human technology cannot approach. The alien hypothesis has not been ruled out by the 2017 data. It has been constrained. The structures would need to be associated with significant dust, but it remains, in the strict logical sense, consistent with the observations. Jason Wright has continued to engage publicly and scientifically with the alien hypothesis throughout the years since the story broke, maintaining the position that took some professional courage to state in the first place, that the hypothesis deserves to remain on the table as long as no natural explanation fully accounts for all the observations. He has not become more certain that the explanation is alien. He has remained careful and honest about the uncertainty, in the same way Boyajian has remained careful and honest. Both of them have been caught in the strange position of being associated publicly with a story about aliens, having their names and their star appear in breathless headlines about extraterrestrial civilization, while doing the unglamorous work of carefully ruling out explanations one by one and writing up results that mostly say, "We observed this, we cannot fully explain it, here are the constraints, here is what we need next." That is what science looks like from the inside. It looks like uncertainty and careful language and not knowing. It does not look like what the headline said it looked like. Boyajian moved from Yale to Louisiana State University, where she continues to study Tabby's star and maintain the monitoring campaign. The star has continued to produce dipping events, and each one provides additional data. She has built something that resembles a small community around the object, a network of professional and amateur astronomers who monitor it, share data, discuss interpretations, and collectively try to solve the problem. The Planet Hunters volunteers who originally flagged the star have followed the story over the years, some of them remaining actively involved in data analysis. There is something genuinely beautiful about the continuity of the people who found this thing being still connected to the effort to understand it. The Kepler telescope itself is gone now. It ran out of fuel in October 2018 and was retired. Its successor, TESS, the Transiting Exoplanet Survey Satellite, has a wider field of view and different observational cadences, and it has observed Tabby's star. TESS confirmed dipping behavior consistent with what Kepler saw, providing independent verification that the behavior is real and ongoing, not an artifact of the original Kepler mission. The James Webb Space Telescope, with its extraordinary infrared sensitivity, offers the possibility of new observations of Tabby's star at wavelengths and sensitivities unavailable before. If warm or cold dust is responsible for the behavior, JWST should be able to characterize its properties in ways that ground-based and earlier space-based observations could not. Proposals to use JWST time to observe KIC 8462852 have been discussed in the community. The star remains active and observable and scientifically important, regardless of what the ultimate answer turns out to be. Because the truth is that Tabby's star is important even if the explanation turns out to be comets. It is important because finding something unprecedented in a dataset of 150,000 stars and being unable to explain it with any known physics is always important. It is important because it demonstrated that citizen science, regular people clicking through data on their laptops at home, can find things that automated algorithms miss. It is important because it showed that the scientific community could mobilize rapidly and collaboratively around a genuine anomaly, pooling telescope time and data and interpretations across institutions and borders. And it is important because it put the alien megastructure hypothesis into peer-reviewed scientific papers and serious academic discussion in a way that was intellectually honest and methodologically sound, demonstrating that the scientific method is capable of engaging with even the most extraordinary hypotheses as long as the evidence demands it. The cultural moment of 2015, when alien megastructure was trending on Twitter and morning television anchors were saying the words Dyson sphere without giggling, was in retrospect an interesting one for the relationship between science and the public. Science communication normally involves scientists explaining things they understand to people who do not. The Tabby star moment was different. It involves scientists standing in front of the public and saying, "We found something we do not understand. We have hypotheses but no answers." The alien hypothesis is on the table alongside the natural ones. We do not know. This kind of honesty, this public acknowledgement of genuine scientific uncertainty at the frontier, is rarer than it should be, and the public response to it was, after the initial excitement died down, mostly positive. People were interested not just in the alien angle, but in the mystery itself, in the existence of a star that broke the rules, in the image of a school teacher and a group of volunteers staring at light curves at home and finding something that the best telescope in the world's automated systems had missed. There is a version of this story that gets told sometimes as a parable about the dangers of hype. The alien megastructure story got out of control. The headlines were irresponsible. The public was misled. And when the resolution turned out to be probably dust, the whole episode made science communication look bad. This version of the story is not entirely wrong, but it misses something important. The misrepresentation happened in the gap between the papers and the headlines, not in the papers themselves. Boyajian's paper was careful. Wright's paper was careful. The scientists were careful. What was not careful was the interpretation layer, the journalism and the social media. And that is a problem that exists in science communication generally, not something specific to Tabby's star. And the scientists themselves in how they handled it. In Boyajian's patient, decade-long engagement with the data, in Wright's intellectually honest refusal to either hype or dismiss the alien hypothesis, modeled something worth emulating. There is also a version of the story that is still being written because the mystery is not resolved. The dust hypothesis is the leading explanation for the short-term dips, but the long-term secular fading, if real and not a calibration artifact, is not obviously explained by dust alone. The infrared situation is not neatly resolved. The sheer scale and complexity of the dipping behavior over the Kepler era, and the absence of any other star in the Kepler field showing anything remotely similar, has not been fully accounted for. The answer, when it comes, may be a combination of factors, more than one physical process contributing simultaneously, in a configuration that is not exotic by itself, but is extraordinarily unlikely to have produced exactly the pattern observed. Or it may turn out to be something that has not yet been proposed, something that requires a new understanding of the stellar environment or the debris distribution around stars of this type. Or, and this remains non-zero, it may be something else entirely. The people who found it deserve a moment here, because they tend to get lost in the story of the star. Tabitha Boyajian named the star for herself, or rather the internet named it for her. And while there is a touch of the absurd in having your professional legacy potentially attached to the word aliens, she has handled it with a grace and steadiness that reflects well on her and on science. She followed the data. She published what she found. She said what she did not know. She raised crowdfunding money to keep watching a star that the major telescope facilities were not designed to persistently monitor. She built a community around an anomaly and kept it going for a decade and counting. These are the things scientists do when they are doing it right, and she did them in circumstances that were considerably more chaotic than most scientists face. And the Planet Hunters volunteers, the thousands of people who spent their evenings clicking through light curves, deserve the same acknowledgement. Science has a mythology about the solitary genius making the great discovery, But the reality of modern science is collaborative and distributed, and the discovery of Tabby's star is one of the clearest examples of how valuable the contribution of non-specialist, non-credentialed but attentive and curious people can be to the advancement of knowledge. They found it, they flagged it, they talked about it in a forum, they said it was weird. They were right. And when Boyajian needed money to keep watching it, thousands of them gave it. This is not what the textbooks describe as the scientific process, but it is what the scientific process actually looks like at its most human and collaborative. The star is still there. It is dimming and brightening and dimming again in whatever complicated pattern its hidden geometry produces. Telescopes are still watching it. Papers are still being written about it. The mystery has not been solved. It may not be solved soon. The universe has been doing something strange around one particular star for at least a century of human observation, and probably much longer, and whatever is happening up there does not particularly care about our timelines for resolution. It will continue to happen at its own pace, and we will continue to watch, and the data will accumulate, and eventually, maybe in a year, maybe in a decade, maybe longer, the picture will be clear enough that the explanation becomes unavoidable. Until then, KIC 846285 sits in Cygnus, 1,400 light-years away, going about its mysterious business. On any clear night, with a small enough telescope or even good binoculars, you can find the constellation Cygnus and point in the right direction, and know that somewhere in that region of sky there is a star doing something no other star has been seen to do. Something that has stumped the astronomical community for nearly a decade, something that in 2015 made the entire world stop for a few days and ask whether we might be looking at the work of another civilization. The star does not know it is famous. The star does not know that a woman named Tabetha Boyajian spent years of her professional life trying to understand it, or that thousands of volunteers found it on their home computers, or that an astronomer at Penn State said the word aliens in a peer-reviewed paper and meant it seriously, or that the internet went briefly electric with the possibility of something extraordinary. But we know. And the knowing, the act of looking at something we cannot explain and keeping the investigation going, honestly and carefully, without forcing premature resolution, without either declaring victory or walking away, is one of the most important things we do. It is what the search for understanding looks like when it is being done well. Patient, uncertain, ongoing, eyes open. The most mysterious star in the galaxy is still out there, and we are still watching.